All right, everybody, thanks for joining me and welcome to edition 3 of the Rocky Mountain Biological Lab Spatial Data Science webinar series. This is a session that's really focused on drones, and we're really focusing on today how to use drones effectively in potentially very challenging environments. And I've got a presentation that's going to last probably about 50 minutes. And then we're going to do a quick 20 or 30 minute demo flight planning exercise. And then that'll be a wrap. We have some materials for the webinar that are posted on the GitHub site, which I'll link to it should be linked in the emails that you got to get here. If you want to follow along, you're just going to need to download those scripts and potentially open up a map that's on that site in QGIS. But without further ado, I'm going to go ahead and share my screen so we can get up and running. All right, can everybody see my presentation?
Yeah, I can see it.
Thank you. Excellent. All right. So I want to emphasize again, this is the third of 6 planned webinars that are going to continue this spring. This session is really focused on designing and executing drone flights. And then we've got another webinar coming up next month that's going to be very focused on something that's a little bit different, which is actually processing the data. How do we get from drone data to scientific insight? And so this is going to be kind of broken up. So today is really about how do we get out in the field and collect a decent, repeatable drone data. And but before we launch into that, I just wanted to talk a little bit about myself. I'm a research scientist at Rocky Mountain Biological Lab. And for the past 3 years, I've been instituting a drone program to monitor plant phenology, or the timing of plant growth and development. And I've learned a ton over the last 3 years in terms of how to mount and execute successful field campaigns using drones. And this is my attempt to kind of boil a lot of that stuff down into stuff that means that you guys won't have to make the same mistakes that I did. And so the structure of my talk is basically we're going to talk about why drones, what do we need to know about drones, and how do we execute field campaigns using drones. And more specifically, I'm really going to talk about why this is a good time to pay attention to drone technology and invest the time and skills into trying to figure out how to incorporate it into your own research program. I'm going to talk about what foundational concepts you need to know to collect good drone data. I'm really going to skim the surface of a lot of this stuff. I think if you really want to dive in, this is sort of a multi-day workshop thing that we're hoping to institute in the summer or fall of 2021, COVID willing. I'm going to talk a little bit about what changes are coming for drones in the near future. And this is both what's happening on the technological side. This is a very fast-moving space. And also what's happening in the regulatory environment, because it is crazy right now. I'm going to talk in particular about common pitfalls of drone data and how can you avoid them. And then finally, I'm going to, practically speaking, demo how to use R and Lychee, flight control software, to design a robust drone data collection. All right, so why drones? Why now? This is basically the reason. So we've got a ton of different ways of looking at the Earth now. Sensors from space-based platforms. This is an image from Sentinel-2 from earlier this summer. And this is a European Space Agency Earth observing satellite that takes pictures of the Earth's surface and returns to the same spot about every 5 days. And this is a tremendously sophisticated instrument that's a powerful telescope pointed at the Earth, but space is really far away. So this is a true color image of Gothic town site. You can kind of see the road that's coming up from south to north here. But at least as far as satellites that image the entire Earth at a decent clip, we are limited to fairly blurry images. But if we take things into our own hands with drone data, there's really not much limit on the resolution of data. And I'm a landscape ecologist and with a primarily field orientation. So whenever we get into a situation where we can start to see, we can start to see individual plants in this image, that's where I start to get really excited. We can then start to link up field measurements much more effectively with remote sensing. So that's just a really great reason why you want to get into drones. The other reason is that this is becoming fairly mature technology. So the platforms are robust, they're inexpensive, they can be inexpensive, and you've got just a lot of choices in terms of sensors and processing software. All right, but beyond just regular images, you can actually collect really sophisticated scientific measurements of plant health, plant cover, and plant stress. So this is an example of a vegetation index called NDVI for, this is a vineyard, I think in Napa, California, taken a couple of years ago. And this is with what's called a multispectral sensor that captures information, both visible light and also near infrared. On top of that, we can actually now mount hyperspectral instruments to drones that capture data in hundreds and hundreds of spectral bands. You can think of those as colors. And those are really powerful for identifying individual species, individual geologic materials like minerals. And that's just like kind of the frontier of UAV sensor technology. Unfortunately, it's still expensive and kind of clunky. I've been waiting for those costs to come down for a while, but so far, no luck. One of the things that's important is that you can actually get really good 3D information from drone imagery as well. So this is an example of a series of digital topographic maps that were generated for a hillside in North Carolina, showing how the growth of crops affects the flow of water across the surface. So with ordinary drone imagery, we don't need a special fancy sensor. We can just use a regular camera. Then we can use techniques to reconstruct the 3D geometry of scenes, including topography. This also works for vegetation. So we can come up with 3D point clouds of vegetation structure, very similar to what you might have seen from LiDAR, just with images, just with processing two-dimensional images. We can take this 2D and 3D information now with the rise of machine learning. We can use those images in object detection. In this case, this is from my own work. We're using really high resolution imagery to identify individual flowers in drone images and then use that to reconstruct landscapes of floral resources for pollinators. Increasingly, we're seeing all of these different techniques integrated into I guess we'll call it integrated sensing and analytics frameworks. And the things that are really driving this are industry. So in surveying and inspection, we have drone-based workflows where companies will contract with construction firms, surveying firms to develop very detailed 3D reality models of construction sites, of bridges, of towers, things of that nature. And on the agricultural side, there are a bunch of companies that are selling services to farmers that integrate drone data, satellite data, and use machine learning to track yield, plant health, and plant stress. So those of us in the environmental research community, for the most part, we're using tools that are developed for these surveying, inspection, and agricultural use cases. So if you want to understand the landscape of drone platforms and drone sensors, you really need to understand that they're mostly serving these two very large markets. The challenge for using drone data in science is that we really want data collection that's simple, repeatable, and reproducible. And that's a real challenge with drone data. For something that's as simple as a digital terrain model that we want to generate from drones of a given spatial resolution with a given accuracy requirements, spatially and spectrally, there are just a ton of different factors that affect the quality and the sort of properties of that data, including aspects of the camera, aspects of how we set up the drone flight. And those are affected by what's going on with the drone itself. And those in turn are affected by the both the physical environment, things like sun angle, cloudiness, things like that, in addition to aspects of the software environment, like what platform we're using, what sensor we're using, what software we're using to control the drone. So it is my goal today to cut through some of this complexity and focus on, what are the key things that you guys need to know for successful drone data collection. All right, and that brings me to the next section, foundational concepts. What do you need to know? And I'm going to break this down in what are the foundational concepts you need to understand drone platforms and sensors? What are the key concepts that you need to understand the processing of drone data? What are the foundational concepts that you need to know about the regulatory environment that affects when we can fly and how we can fly? All right, drone platform fundamentals. We can break things down into basically two different types of drones. We have multicopters, which are essentially just small unmanned helicopters. They can have 4 rotors, they can have 6 or 8 rotors. And these are relatively stable, relatively maneuverable, and they have a capability to take off and land vertically. This vertical takeoff and landing is called VTOL. The trade-off there is that they're relatively slow. And in practice, what that means is that a survey with a multicopter can just can cover less ground in a given amount of time or a given amount of battery than the type of drone we're going to talk about next. And these are fixed wings drones that are fast, long-ranging, and less stable. And up until recently, the fixed wing drones, mostly you had to figure out a way to clear off a landing area for essentially a runway, not necessarily for takeoff. Some of these you can actually launch with your hand by throwing them. But they needed somewhere to land. But that's becoming less of an issue. A lot of these fixed wing drones are actually starting to learn how to take off and land vertically, like this Wingtra 1 drone, which is the orange one in the bottom right. That's a very, I guess, well-proven vertical takeoff and landing fixed wing drone. And as far as the overall costs of these platforms, they really range a lot for both multicopters and fixed wing. From the low end, we've got kind of consumer drones that people use for taking rad videos of themselves mountain biking, all the way up to high-end commercial platforms. So the left-hand drones are on the order of $1,500 to $2,000. The right-hand drones are on the order of $15,000 to $2,000. And so there's a huge range of investment. Generally, what you get for more expensive drones is you get more flight time, you get very precise survey-grade GPSs, which is going to be important for saving time on georeferencing imagery, and they can also carry more payload. So the multicopter on the top right is the newest multicopter by DJI, and that can carry a payload of about 2 kilograms before it starts to really hammer the flight time, as opposed to the really tiny drones off the left that really can't carry much that's much more than a GoPro-sized instrument. For sensors, we're really mostly talking about passive sensors. These are sensors that just take imagery, electromagnetic radiation from the surface and record how much of that impinges on the sensor. This is the electromagnetic spectrum. You can probably remember this from high school physics. On the far left side are long wavelengths. You can think of those as radio, radar, microwaves. All the way to the right-hand side are really short, high-energy wavelengths, cosmic rays, gamma rays. And for the most part, what we're looking at is a narrow band of energy ranging from near infrared to visible light to ultraviolet. And for passive sensors, that's really important because that is actually where most of the sun's energy comes into the land surface. So if we're trying to record that energy with a camera, we'll want to be focusing on these relatively narrow bands of energy. So this is really where most of the action is, visible and near infrared. There's another reason why we want to focus on near infrared, mostly for environmental research, and that's that plants reflect a ton of near infrared. So this is a near infrared photograph taken of a Christmas tree farm by the photographer Lisa Comorley. One of the things that you'll notice here is that the vegetation is super, super bright. And that is essentially because this energy, this near infrared energy, is useless for photosynthesis, but it heats up plant leaves, so they want to get rid of it. And that means that vegetation that might look dark, in this case it would look dark green in visible light, is super reflective in near infrared. And that means that infrared wavelengths are super important for measuring vegetation, for essentially separating vegetation from soil and rock and other materials, as well as assessing plant health. Because as soon as one of these Christmas trees starts to get stressed or die, its near infrared reflectance is going to start to go down. And so those sensors that are sensitive to visible and near infrared light are called multispectral sensors. And that's really where a lot of, I'd say maybe 90% of the drone data that's collected is with these multispectral sensors. I'm not going to talk about this a lot, but there are a class of active sensors that actually take energy and emit it from the sensor, bounce it off the land surface, and return it and record what returns. These are LiDAR and synthetic aperture radar. They have specific applications for cutting through dense vegetation to map topography and doing things like mapping snow, water, and soil water. But these are, for the most part, expensive and fiddly instruments that really haven't gone into the mainstream. So they're active points of research with drones, but like I said, about 90% of the sensors you see are these multispectral cameras that are passive sensors, not active. Okay, data processing fundamentals. If we've got one of these multispectral cameras, it's essentially just a camera that takes 2D images, not too differently from the one that is in your cell phone or in your DSLR camera that you use to take pictures of your kids. What makes this interesting is that we're moving the camera around and taking a bunch of images from different perspectives. And this allows us to reconstruct the 3D geometry of a scene using a technique called structure from motion, which just means reconstructing 3D scenes from 2D images. And this is possible because of computer algorithms that were invented about 15 years ago for automatically identifying common points in adjacent images. So in this case, we've got 3 different images of this cube, and they've got different corners. The two that are labeled Q1 and Q2, or sorry, Q1 and QJ. Q1 appears in multiple images of that object. And if we can come up with an algorithm that efficiently identifies Q1 in all those different images, and we know where the positions of the cameras were, then we can triangulate the position of Q1, QJ, and the other tie points in this image. And if we have enough of those common locations, then we can reconstruct the full 3D geometry of the scene from those 2D images. This is important because when we take images from the top down, we're actually getting we're not getting a true sort of mapped view of the scene. If we look towards the edge of a photo, it's viewing the land surface at a slightly different angle than the middle of the scene, even if the camera is pointed straight down. So we need to do something called orthorectify the image, which is to you can sort of think about that as undistorting photos to get a top-down view. And conceptually, what this means is that we're draping the imagery that we have over the digital surface model and then reconstructing that sort of plan view. The orthophoto is a view of the surface where every point along that surface, we're seeing the exact top-down view. This is, I think, become kind of routine to think about, because when you look at an aerial photo on Google Maps, you're not looking at a photograph, you're looking at an orthophoto, which is an orthorectified map, which is processed from a bunch of different photos using this structure from motion technique and a digital surface model. The important thing is that we need good 3D data to get good 2D data, and that'll become more clear why that is a little bit later. Okay, so that's platforms and sensors. Let's talk about drone regulation. So the important thing is that the airspace is regulated by the man. We don't have private property rights in airspace, It is all, you can sort of think of that as not necessarily owned by the government, but at least regulated by the government. That means the Federal Aviation Administration in the US. And flying for research is considered commercial use by the FAA. And what that means is that there are a couple of additional requirements in addition to recreational, the requirements for recreational pilots, and that includes a certification process for remote pilots. It's not too bad. It essentially means that you need to pass a knowledge test that's 80-question multiple choice, pay a fee to take that test, and do some background reading to get up to speed on the regulations around drones that the FAA puts into place, and also just how they regulate airspace. How can we figure out where we can and can't fly? In particular, flights are restricted to certain conditions. And I don't have time to go through all of the regulations, but there are a couple that are really important that I wanted to highlight here. The first is that we need to maintain what's called visual line of sight with the drone. So if we can't see it, we are in a situation where we're violating FAA regulations. They don't want people to lose drones out in the ether that could potentially be interfering with aircraft or doing things they're not supposed to. And if we can't see them, it's difficult to actually know whether that's happening or not. The second one is that they're restricted to 400 feet above ground level. And that's just to keep drones from interfering with regular aircraft that are supposed to stay above 500 feet in general. We also can't fly at night, and we can't fly in situations of adverse weather. We also can't fly, for the most part, near airports unless you have unless you get a special waiver from the FAA. And all these regs are part of what's called FAA Part 107, which regulates that commercial use of drones. Now, this is sort of the regime that's been in place since 2016, and that's actually going to be changing in the next few years. So I'll be returning to this regulation side of things in a minute. Okay, so what changes are coming for drones in the near future? I just sort of explained a little bit about the current state of things. What's coming out? And I'm going to talk a little bit about the technology, because that's exciting and rapidly evolving, and also a little bit about the regulations that are coming in. Okay, the first trend that I see is that we've seen more and more what are called hybrid fixed wing designs. The distinction between multicopters, which are essentially just unmanned helicopters, and fixed wing drones, which are essentially just model aircraft, is starting to go away. And what that means is that you've got drones like this Wingtra 1, which can take off and land vertically. So they have a lot of the advantages of helicopters. But they also have the advantages of fixed wing aircraft. They're more efficient in flight than helicopters are, multicopters are. And they can fly faster. They can fly more area in a given battery. So the commercial drones that you've got that are multicopters have a flight time that maxes out at about 45 or 55 minutes. And these fixed wing drones like the Wingtra 1 max out at flight times of more than an hour. And that really does make a big difference if they're almost twice as fast and they can stay in the air for almost 25% or 30% longer. That means that they can potentially map larger areas in a given amount of time than multicopters. So keep your eyes open for this space. The second thing that I wanted to highlight is that there's a trend toward integrated sensor packages. And that means different types of sensors that are all packaged together in ways that allow data collection of multiple types at the same time in the same flight. So an example of that is a new sensor that's coming from the company DJI. This is called the L1. And this is a solid state LiDAR sensor. So it's a laser scanner that allows you to map topography and vegetation structure very effectively, coupled with a very high resolution RGB camera. And when you fuse that information together, it actually allows you to come up with a true color point cloud, which represents data from both the LiDAR sensor and the RGB sensor. That's pretty exciting. I think it's kind of fun that this sensor in particular owes its existence to self-driving cars. So the LiDAR, the company that makes the LiDAR is called Livox, which is uses a new solid state technology, which the primary market for is actually in vehicles, in advanced driver assistance system for vehicles, and this is sort of just an unanticipated benefit that the costs of UAV-based LiDAR are coming down. This is another integrated sensor package. This is a MicaSense Altum. So the 5 big lenses that you see are regular cameras that are sensitive to red, green, what's called red, green, blue, red edge, which is between red and near infrared, and then infrared. And then the 2 small openings that you see there are for a thermal sensor. So it also can give you essentially a picture of both the structure and a little bit about the function of vegetation. Because plants cool down when they transpire, it allows some cool applications for actually monitoring plant physiology in real time using drone data. So that's exciting. Another trend that I see coming in is we've got much cheaper, high precision GPS coming down the pipe. So these are systems called RTK, or real-time kinematic GPS. And the standard GPS on most drones is accurate to within a few meters. And that's really not sufficient for high accuracy drone maps. But the survey grade GPSs on some of these newer drones are accurate to within a centimeter or 2. And what that means is that we can essentially process the data and get good geolocated maps without having to go through an extensive process to install ground control points and then geolocate them really effectively and find them in imagery. This is pretty exciting because it potentially makes drone data collection in the field almost twice as efficient. So there's a bunch of companies that are in this space. The established companies like Skydio and DJI have been around now for 10 years or so. There's a bunch of new startups like Skyfish, Black Swift, Vantage Robotics that are developing really interesting platforms and sensors. So it's just kind of a fun thing to see what's coming out as these technologies evolve. What I will say is, if you're a researcher and you're interested in data collection over multiple years, long spans of time, some of these multispectral sensors and some of these drone platforms are probably going to be around for a while. So you should always kind of look for the new stuff that's coming out. But I think that a lot of the, particularly the sensors like this MicaSense Altum sensor that are going to be really useful for agricultural purposes, they're going to be selling that for a long time. Okay, the other thing that I want to mention about technology is that the flight time and mapping area of drones is almost entirely tied to lithium-ion battery technology, and that continues to improve every year. So this is a plot from 2006 to 2020 of just the energy density of lithium-ion batteries. And energy density is the amount of electricity, essentially the amount of juice per kilogram that a battery can store. And over the past 10 years or so, that's been going up by about 6% a year. And that's likely to continue. Again, it's not driven by the drone market specifically, it's driven by electric cars. And so a lot of the technology that's driving lithium-ion battery chemistry forward then filters back into the drone market. Okay, so that's technology. Let's talk about regulation. So just in December 2020, there was a new set of FAA rules that were published on the Federal Register that change how drones are going to be operated in the future. And there are 2 new things that happened here. The first rule is called remote identification. And the second one is it changes, there's a new rule that changes the restrictions about operations over people. The most important one for our purposes is this remote ID rule. Forever, I guess forever means since 2016, the situation has been that you needed to register your drone with the FAA, but it didn't need any particular means of communication with any other entity but the person who controls the drone. What the FAA is instituting is the capacity for drones to transmit their position to other aircraft. And that's going to be really important as drones start to get used for delivery purposes, beyond visual line of sight at night, these other cases that have been restricted in the past. If we have a system for identifying drones and avoiding collisions with between drones and piloted aircraft, then we can do a lot of new things. And what that means is that drones that are compliant with this new rule need to be able to broadcast their identification, essentially where the drone is, how fast it's moving, how high it is, and also, and this is important, where the operator is, and a unique code that's associated with both the drone and the operator. This is information that is just kind of sent out into the air. So if somebody like a law enforcement personnel has the right receiver, they would be able to figure out what drone, like whose pilot, or I guess what the location of the pilot is of a drone that's doing something it shouldn't. And that's, I think, pretty important and a positive thing on the enforcement side of things. What it does mean is that this new technology is going to have to be integrated into drones, and it can happen either one of two ways. You can have remote ID drones. These are new models that have built-in Wi-Fi or Bluetooth sensors transmitters for transmitting the information that the FAA requires. And there's also potential for add-on modules that would broadcast this information. Those requirements are, I would say, pretty modest. There was an initial proposal to have this national network of drone logging information that would require drones to transmit signals to cell networks, so FAA would have real-time data on where all the drones in the nation are. But that didn't really fly. So the new rule has these kind of modest new requirements, and those come into effect June 16th, 2023. So it gives the industry a little bit of time to adapt. But if you're thinking about investing in a drone for the long term, like we have, it's something to keep in mind. The other thing on the regulation side of things is that there are new restrictions on US export to Chinese drone companies. The Commerce Department recently put out a statement saying things that these companies pose a significant risk of being or becoming involved in activities contrary to the national security or foreign policy interests of the United States. Essentially, we're getting caught up in geopolitical conflict between the USA and China. And as a result, the federal government is really cracking down on Chinese drone companies. The company that has the most to lose in this battle is DJI, which owns about 75% of the commercial drone market in the United States. What it does is it doesn't ban the import of DJI drones or the use of DJI drones in the United States, but it does prevent DJI from sourcing its technology from US companies, and that could affect its supply chain. So in the short term, this is not going to be very disruptive to customers using DJI drones. Like I use DJI platforms in my own work. But in the long term, we have to think about whether these restrictions are going to get more severe. I imagine that sort of great power competition between the US and China is not going away anytime soon. And there's a real chance that there's going to be more import restrictions on Chinese drones in the future. So it has a lot of us who are used to using DJI drones thinking about what can we do to reduce our risk of not being able to get parts, being able to get drones from Chinese companies. Okay, so that's what's happening in the regulatory and geopolitical space around drones. I want to talk a little bit about pitfalls of drone data. It is relatively easy to go out and fly a drone and collect imagery. It is relatively difficult to go out and fly a drone and collect good scientific data. So I'm going to go over some of the common pitfalls right now. The first one, and I think the most important one for planning, is insufficient image overlap. So remember, in order to get good maps, we need to process individual images into what are called orthomosaics. And in order to do that, we need lots and lots of pictures. And those pictures need to overlap with each other so that we can triangulate common points within the images and reconstruct the 3D scene for mosaicing. And so this is just an example of 3 different levels of overlap. Up at the top, there's images that are taken with no overlap on the ground. Midway down, I think this is about 20% overlap, and further down is about 70% overlap. So this is, I think this is kind of a funny example, because actually all 3 of these levels of overlap are usually insufficient. For the most part, we want drone data, we want pictures to be taken with at least 75% overlap for regular drone data collection. And if we're working with complex vegetation, including forests, that needs to be even higher. So this is a cool figure from a paper from Frey et al. A couple of years ago. So the red points are, sorry, the blue points are the red points are the 3D points, the common points that the processing software is going to use to stitch the photos together into a map that we get from 61% image overlap. And then the blue points are the additional points we get with 80% overlap. And one of the things that's important here is that you just have a ton more points with 80% overlap, and you also have a ton more points below the forest understory. So this is just kind of a cross section through one flight line, and without the extra overlap, you don't really get much coverage in between individual trees, and that can make it actually really tough to figure out where the ground is in 3D models that are derived from drones. So the more complexity that you have in your scene, the more overlap you need, and the more images you need to get a good reconstruction. A second potential pitfall has to do with terrain. So if our scene is totally flat, then this isn't an issue. But if we're flying on a slope or our scene has a big hill or some other large object in it, we're going to need to adapt the flight paths to follow the terrain. Otherwise, there's going to be different amounts of overlap in different parts of our scene. So in this diagram, the low part of the terrain off the left-hand side, you've got a little bit of overlap between adjacent images, although probably not enough to have a successful mosaicing scenario. But that gets even worse as the terrain gets closer to the drone and the drone doesn't follow the terrain, because the field of view goes down as the distance between the ground surface and the drone gets shorter. So when we're planning flights in steep terrain, we would need to pay attention to this issue. And the last thing that I want to talk about on the planning side is the battery safety margin. It's typical to think, okay, so my drone can fly 25 minutes before changing batteries. So I just need to design a flight that's going to take 24 minutes, and then I have plenty of time to come back and change the battery off for the next flight. But that's really the things that are on the spec sheet of the drones are idealized situations. And that means sea level with no wind and no payload. This is particularly an issue in high mountain environments. And that's because pressure and density of air goes down pretty quickly as you go from sea level up into the atmosphere. So up in Crested Butte, Colorado, where I work, we're at about 3,000 meters of elevation, which means that air is actually only about 65% as dense as it is in sea level. And because drones fly essentially by forcing air down, the less momentum and the less density that the less density that air has, the less momentum it has, and the less efficiently drones can fly. So in practice, that means that a drone like I use, like the Mavic 2, can fly for about 35 minutes at sea level, but only about 22 minutes at 3,000 meters, and then only about 18 minutes at 3,000 meters with an extra IR camera strapped to it. So keep that in mind. And so finally, on the planning side of things, it's just easy to crash into stuff. And you gotta, for a given flight area, scope things out to, in particular, figure out how to avoid wires and trees. Most of these drones have pretty good obstacle avoidance sensors. So they have cameras that prevent them from running into buildings and other solid objects. Those don't always work as well for really thin objects like power lines or trees without vegetation on them. So this is an unfortunate soul who's gotten his drone actually stuck in a tree. That's perhaps a better scenario than what typically happens, which is just the drone just crashes. This is actually not easy to do, but it's not hard to do either. So anytime that you're scoping out an area for a drone flight, you gotta, I almost always say you have to go out there and see it, because you can't always see wires and other obstructions in the imagery you get from Google Maps and things like that. Okay, so to avoid those pitfalls, here are the 4 things to keep in mind. You want to plan flights with a lot of overlap. at least 75% for most scenes, more than 80% for forests or complex topography. You want to plan flights that follow the terrain if the elevation changes are greater than 10% of the flight height. You want to scout for obstruction and line of sight before planning a flight. And you want to plan flights for less than 2/3 of the battery life or endurance of a drone. And that 2/3 rule of thumb works pretty well unless you're designing a flight to go out and repeat it over and over and over again. So I have a bunch of sites that I visit every week and fly to monitor plant growth and snow and some other stuff. And I have flights that I want to be able to complete those flights even in relatively adverse conditions. So if there's high winds or cold temperatures, both of which affect the life of the battery, I still want to be able to complete that flight. And that means that for my flights, I take this down I plan my flights for 1/2 of battery life. And that means I can almost always carry them out in decent conditions. Okay, so those are planning pitfalls. Let's talk about execution pitfalls. The first one that I'll talk about is poor ground control. So remember, we're reconstructing 3D scenes using this drone imagery. And that's only possible if we know at least approximately where the cameras are pointed. Otherwise, we have no way of knowing where in the world the imagery comes from. And the way that we do that in practice is that we go out into the field and we put out reflective disks that show up in the imagery. And we go back in software and we identify where those disks appear in the image. And because we've got really accurate GPS points for the disks in the field, then we can use that to make good georeferenced maps. In practice, we need a lot of ground control points to get good performance. And we need those ground control points to be pretty accurately geolocated. So we need lots of them, and we need them pretty evenly distributed across the scene. For the most part, your cell phone GPS is not sufficient for getting good performance here. And so what I use for a lot of my work is an antenna made by Trimble. This is a Trimble Catalyst antenna that in good conditions gives me locations that are accurate to within about 10 centimeters. And that's adequate to my application. If you really, really needed centimeter accuracy for, say, monitoring snow or some kind of surveying task, then you'd probably want to get a survey grade rig for your ground control points. You'd also want to make sure that there are a lot of them. So, oops. This is a plot from a 2016 paper that looks at the amount of error in a reconstructed elevation map that's as a function of distance from the nearest ground control point. So if you've got if you're really close to a ground control point, you've got relatively low error, but that increases relatively pretty steeply and non-linearly as you go from close to about 250 meters away from a point. So the more points you have, the more coverage you've got, the more parts of your scene are close to a ground control point, the better geometric accuracy you've got on your mosaics. Okay, there are a ton of issues associated with illumination. The bane of my existence are clouds. So cloudy conditions are okay, sunny conditions are okay. But if the illumination changes during the flight, in this case, there's a cloud shadow that you can see on the bottom left-hand part of the image, then that affects the radiometric, the scientific accuracy of the data that we collect, and that's usually no good. Another problem to keep in mind is low sun angle. So this isn't such an issue in the summertime where we can choose to fly in the middle of the day when sun angles are really high and shadows are really short, but especially in the fall and the winter, you can get into situations like this where if we want to figure out where snow is, we have to essentially look for snow in the sun, and then we have to also look for snow in the shadow. And those two different conditions, sun snow and shadow snow, have different spectral signatures, which makes it kind of hard to map them. So sometimes this is unavoidable, but you usually want to fly with high sun angles and relatively short shadows. Sun angles can be too high, however. If you fly really close to solar noon, then you start to pick up specular effects in the imagery. So this is an example. You can kind of see a pretty distinct line of white or light colored dots that kind of go from the bottom right to the top left of this image. And these are essentially sun glints off of leaves, because leaves are more reflective if you, they're sort of more reflective directly if you're sort of in between the sun and the plant leaf. This is also true for soil, though to a lesser extent. What this means is that if you fly at solar noon, especially in tropical environments or in the middle of summer, you can get some of these specular effects in your imagery and get stripes. So that's something to keep in mind. Also, camera settings are complicated. This is an image histogram that looks at the intensity value. This is essentially how bright the red, green, and blue channels are on a regular RGB image. This is a I guess, this is an example of a sort of well-calibrated image. You've got a lot of data sort of in the middle of the intensity range and very little data that's near 0 or near 255. But that's only if you get the camera settings right. The important thing is you need to make sure that the speed of the shutter and the width of the aperture, call it f-stop in camera parlance, is appropriate for the brightness of the scene that you've got. A lot of cameras have automatic routines for adapting the shutter speed and aperture to deal with the image that they've got, but that's actually not what we want for the most part with drone data. We want a constant aperture and a constant shutter speed. That way we're looking at the radiance value that's coming off of the surface and not just something that's attenuated by the camera itself. So I don't have a lot of concrete recommendations that I can fit into this presentation, but you just got to make sure that you pay attention to camera settings. The final thing that I'll talk about is operator error. This is complex technology, and we are all sort of Homer Simpson in the nuclear plant on this. And the way that we deal with that complexity is really just with checklists. None of the things that we do to collect drone data is necessarily complex if you break it down step by step. The steps are simple, even if the whole is complicated, and checklists are your friend in that. Okay, so to avoid execution pitfalls here, we want 7 to 10 ground control points per mission at least, geolocated to less than 30% accuracy and visible in the imagery. We want to avoid partly cloudy conditions and fly within a couple of hours of solar noon, but avoid that sort of 30 minutes around exact solar noon. We want to test and check the camera settings before the flight, and that's one among many things that we want to checklist. So I've actually shared on the GitHub site all the checklists that I use for my drone data collection, and I'm hoping that those will be helpful for you guys. This might bring up the overall question: do I want to do this myself, given all the complexity? And I guess the answer is you should, if you're willing to put in some effort. I'd say that it took me about 6 months to really get the data collection and processing workflows dialed in for my work. And that I think is worthwhile if you're willing to put in the time and effort. But that's not the only solution here. Recognizing that this is complicated technology, one of the things that I've been doing at Rocky Mountain Biological Lab is thinking about, how can we leverage some of the stuff that I've learned over the past couple of years to make drone data collection for other scientists more efficient. And that means in 2021, we're actually offering this on a fee-for-service basis. And this is going to be we're thinking of it's probably a freemium model with limited free missions for Rumble scientists. We're going to set up an application. The details are still being worked out, but you should hear more in February. And then there's additional missions that scientists can request for a per mission fee. And we're still trying to figure out what that structure should be, but it's one opportunity for scientists to take advantage of this drone data without having to solve all of these logistical problems yourselves. That's not saying that you shouldn't also think about collecting your own drone data, and we'll support you in that. But this is just one option for folks who don't necessarily want to dive all the way into doing it yourself. the platform that we're thinking we're going to be using is actually pretty cool. This is a DJI Matrice 300 RTK, sort of the top of the line commercial drone that DJI uses. And I put an asterisk there because I think there is some systemic risk associated with DJI that wasn't there before. And over the next month or so, we're going to be really reassessing whether this is the drone we're going to get. But regardless of the drone, we're going to be pairing it with a top-of-the-line MicaSense Altum. This is a multispectral plus thermal sensor, which should give us good data on the near-infrared and visible parts of the spectrum that allow us to do cool stuff with plants, and also thermal imagery that we can use to map microclimates and plant physiology and other things. So exciting stuff. All right, so that gets us essentially all the way through. And the thing that we're going to do now is I'm going to do a flight demo. So I recognize that some of you guys need to take off after an hour, and that's totally fine. The webinar recording will be up and running. But I'm going to pause really quickly here and take a few questions before I move on to the next stage. All right, so I have one question from the chat, which I actually, I'm sorry that I didn't see before. This is Mark Raleigh's question. What wavelength is this LiDAR, green or near infrared? That's a great question. I think it's near infrared, which is really exciting for mapping vegetation structure. If it's green, then that's still cool, but not quite as cool. That's a great question. Yeah, I guess any other sort of pent up questions that we can address before I move on? Oh, so Natalia says, could you repeat how to avoid the execution pitfalls? Yeah, definitely. Okay, so I really had five recommendations, and that was around ground control points. So we want a lot of them, and we want them to be georeferenced accurately in the field. We want to avoid partly cloudy conditions, fly within 2 hours of solar noon, but avoid that 30 minutes around exact solar noon because we get sun glints in the imagery. And we want to test and check the camera settings to make sure that we're not losing data because stuff's too dark or too bright. And then we use checklists for everything. So checklists for pre-flight, checklists for flight, checklists for post-flight, checklists for planning. Just make sure that you write down all the steps and go over them every time. It's kind of a proven method for avoiding mistakes in all sorts of, in medicine, in the pilot flights and all sorts of stuff. So Ben says, could you discuss UV imaging in a bit more depth? I know we've talked briefly about it. Are imagers going in that direction? It would be great for bird vision, but I can't think of other uses driving the technology. Yeah, that's a great question. So one of the things that I didn't mention is that there are a bunch of companies that are now offering custom sensor packages, essentially meaning that you can glom together sensors that are sensitive to a bunch of different wavelengths, and you can sort of pick the wavelengths. And so the companies that are focusing on UV imaging, essentially there's not a big market for UV imaging like there is for infrared imaging, essentially because UV doesn't give you a ton of information about crops. But for specific applications like Ben's trying to understand how hummingbirds see flowers and other parts of the landscape, having an ultraviolet imager would be awesome. So that the companies that are catering to this market sort of allow you to pick the sensor, pick the filter, pick which wavelengths you want, and go forward there. Those cameras are still relatively expensive compared to the off-the-shelf stuff, but not too bad. So I'd say I wouldn't hold out hope for a cheap sort of off-the-shelf ultraviolet imager, but it's becoming increasingly feasible to get the right camera. All right, Wendy Brown says, can we buy a sensor for you to fly? Yes, I'm glad that you mentioned that. That's one of the things that we want to offer. And that's something we would have to coordinate pretty closely to make sure that that our platform is compatible with the sensor. But the drone that we're looking to get is going to be able to carry a payload that's up to about 2 kilograms, and that should allow us to integrate most of the I guess most of the sensor packages that are on the market to go. So, you know, I think that this is still something that we're working out, but bring your own sensor is one of the things that we anticipate a lot of researchers are going to be interested in. All right, so I'm going to move on to the flight planning demo right now. Thanks for some great questions, guys. Let's see, go back to screen sharing. Okay, so I'm going to take you through planning a flight that's kind of like the ones that we use to monitor plant growth and development. And in general, there are kind of two types of flights that we might want to undertake with a drone, and they're called grid and double grid. And grid flights are essentially just a lawnmower pattern represented by the green line here on the left. And so we're flying back and forth and having the sensor take images at a given interval. Sometimes, yeah, we probably want to get it to take images as fast as it will take, so we get more overlap between adjacent images. But for reconstructing 2D maps, this kind of lawnmower pattern is usually adequate. But if our focus is really on 3D models, then it's more effective to fly a double grid, which is like that lawnmower pattern, except we then turn it 90 degrees and then fly the other lawnmower pattern that's lined up over it. And what that means is it ensures that we're getting views of all different sides of 3D objects. If we've got this regular grid pattern, that works pretty well, unless you've got really dense vegetation. But yeah, if you want to be able to see in between trees, for example, you really need something like a double grid. That's not the case for the site that I've got picked out for our demo flight. So we're going to actually just plan the simplest type of flight, which is a 2D grid. And the site that I've picked out is actually one of the places that I spend quite a bit of time. This is a hillside off of Brush Creek in the Gunnison Basin in western Colorado. And I call this site Deer Creek, even though it's near West Brush Creek, because there's a trail that comes down here that's called the Deer Creek Trail. So we're going to call this the Deer Creek site. And it's an open hillside, which is really very sparsely vegetated in terms of trees and shrubs, but it does have quite a steep topography. So we're going to use a software package called Lychee or Lychee, depending on how you want to pronounce it, to make this flight plan. But the first thing that we need to do, Lychee is great because it gives you a lot of control. The problem is it doesn't give you a lot of help. So we need to first figure out some basic parameters about our flight, namely how close together do these kind of lawnmower pattern swaths of flight need to be, and how high, I guess how high off the ground do we need to fly, and how fast can we fly and still collect the right amount of imagery. And to do that, I've put together an R script that helps to simplify some of those decisions. So if you are following along and you want to bring up that UAV flight planner.r script that's up on the GitHub site, and I can talk you through it. So the core of this this script is a function called calculate overlap, and it's a function that takes the altitude we want to fly, the frequency that we want to take images, the airspeed of the drone, the path distance, which is the distance between adjacent swaths in that lawnmower pattern, And then properties of the sensor, like the field of view and the resolution of the sensor. And it's going to take all of that information and put it together into an estimate of how much overlap we have between adjacent images, and then also what's the ground resolution of the imagery that we're going to be collecting. And so I've got two different sensors that I use for my own. Actually, I've got four sensors that I use, but two mainly for planning. And they're the built-in cameras on two different drones, the Phantom 4 Pro and the Mavic 2. And there we've got the width, the focal length, and then the pixel size, or say the number of pixels in X and Y of that sensor. You can essentially, this is for an RGB sensor, but you can come up with similar measurements for any multispectral sensor that you can imagine. And if we put all of that together, what it means is that we can essentially, by trial and error, adjust the altitude, frequency, airspeed, path distance to figure out whether we're going to be able to get enough overlap in our scene. And so if you run that, you should see printed to the console some information. So it's saying that we're going to be flying at 110 meters, 360.89 feet. So that's pretty close to how the maximum flight height that we can fly and still be in compliance with the FAA regulations. We're going to be flying at 39 kilometers per hour, which is about the maximum that my particular drone can sustain in a light breeze. And then the drone can take images every 2 seconds, or that's 0.5 images per second. And that's going to yield what's called a ground sample distance, or GSD. That's the pixel size of the imagery on the ground, of about 2.5 centimeters per pixel. That's pretty good. I'd say in my work, I need imagery that's about 3 centimeters per pixel or finer, so that seems to work pretty well. And it's giving me an estimate of side overlap of 75% and forward overlap of 77%. So that's great. For this particular flight plan, that's going to work really well. If I wanted, for example, to fly at 40 meters instead of 110 meters, then a couple of things change. The first thing is that the ground sample distance gets smaller. That means that we're getting finer and finer imagery, in this case, less than a centimeter per pixel. But look at here what happens to overlap. Because we're flying closer to the ground surface, our field of view on the ground is much smaller. It means that adjacent images are going to have less overlap, both side to side and front to back. And that means we're actually going to have to decrease the path distance a lot. So that's let's decrease it to maybe 15 meters, and also reduce our airspeed, which affects the forward overlap, down to about 20 kilometers per hour. Okay, so we're still not great on forward overlap, so we can reduce speed to 15. Say maybe reduce path distance to 10. Okay, so now we're finally back in that situation where we've got enough overlap, but the challenge here is that we're able to cover a lot less ground with this flight than we could with the flight before, and that means that our potential flight area for that 3 centimeter resolution on the ground is much smaller than it was for the 1 centimeter resolution on the ground. It's much smaller than it was for the 3 centimeter resolution. So I'm going to go back to the parameters we had before, because that has the approximately the right sweet spot for my particular application. So that means essentially we need to make a lawnmower pattern that has paths about 35 meters apart on the ground. So I can do that in Lychee pretty easily. So this is the interface for Lychee. It's essentially looks a lot like Google Maps, except if I double click on the surface here, it'll add a waypoint that I can then use to navigate the drone to it. So the first waypoint, I usually want to have that exactly at the place that I want to start, and I want to keep away from vehicles and people. So let's put it over here in this willow patch. So when I clicked on that, it added a waypoint here, and I've got some ability to change the parameters of that waypoint. I'm going to change that to 110 meters, which is that height that we wanted to do before. And then I'm going to change the flight speed to, I think that was 39 kilometers an hour. And then I'll worry about the curve size and heading later. But now I can go ahead and start putting out waypoints. So I know in this scenario, at this site, the wind usually comes out of the northwest. And I'm going to align my flight lines with the prevailing winds, because things tend to get a little bit tricky if you've got crosswind. So I want to minimize the crosswind by putting my flights in here. And I know I can see the drone out to about 400 meters. So I want to make sure that if I'm standing here with a controller, I'm not more than about 400 meters from the drone. And then I'm going to start putting that lawnmower pattern in. And you can see the distance of each segment here. And I'm going to change that to about 35. And yeah, so I can just continue to place these waypoints to define the flight lines. And up here at the top of the new flight, you can actually see the total distance of the flight and the total time that it estimates that the drone's going to take to perform the flight. And so I would be able to do this until I got up to about the maximum flight time. So in this case, the maximum flight time is about 18 minutes for the drone and sensor that I've got. So I could potentially put a lot more flight lines in. This is going to be like a cooking show. I'm not going to go through all of this. And instead, I'm actually going to bring up one of the previously saved flights. And so you can see the full. This is the full deal, right? So I've got the flight starts at that site where we were looking at before. It's going to fly the lawnmower pattern with approximately 35 meter spacing between the flights, and then it's going to come back, and the last waypoint is exactly at waypoint 1. You'll notice I've also done a few other things here. So I've added waypoints in between the start and the beginning of each flight line, and that's going to allow us to do the terrain following a little bit better, and I'll get to that in a second. You'll also notice that each one of these icons looks like an eyeball on top of a paper airplane, and now that's pointed in the direction of the flight line. So that's the heading here that I've just set to be approximately the same as the flight line. That means that's going to keep the drone oriented so that it's always flying directly forwards or directly backwards. It can always fly side to side. It's one of the cool things about a quadcopter, but it's less efficient doing that. So you want to get it pointed in the direction of the flight line. I've also added curved turns here on the ends of the flight line, and that's going to mean that the drone actually doesn't have to slow down as much to keep close to its flight line, and that makes it a little bit more efficient to fly those curved turns. Sorry, I got booted out of screen sharing really fast. All right, and you can see up here the total distance here is about 7.1 kilometers. The total time of about 16 minutes. Remember that's below the threshold maximum flight time that I think I can sustain. But here's the problem with this flight is that I've defined a constant altitude, and that's going to be a problem for for this particular site. I'm going to switch out of Lychee Mission Hub and back to a GIS program where I've loaded an elevation map. And you really see this is kind of a steep hill. So if I sample down at the start location, that's about 2913 meters. Up here at the top of the hill, it's like around 2964. So it's essentially 50 meters of difference in elevation between one part of the flight and another part. And that means that I'm going to really need to pay attention to terrain following. Now, Lychee has a built-in terrain following functionality. So if I were to take this flight and check the above ground option, what it's going to do is take the elevation map that it's got in its memory and then use it to update the location of, the height of the waypoint so that it follows terrain. The problem with that is that this is a really coarse resolution elevation map that it's using behind the scenes there, and it doesn't actually tell you that. So I'm not going to get great terrain following results if I use the built-in functions. That might not be such a big deal for a relatively flat topography, but here in the mountains where we're trying to image steep sites, it's enough to make a difference. This would also potentially be a really big problem if I wanted to do super high resolution flights where I was collecting imagery from just a few meters above the ground. I want to be able to skim the surface and not worry that the elevation map is going to be wrong and cause it to crash into the hillside. So to do that, I'm going to actually have to do a little bit more than just play around in Lychee. But one of the cool things about Lychee Mission Hub is that it's pretty easy to import and export data. So what I'm going to do is go to missions here and export as CSV. And then it's going to download a copy of that. Oops, I don't want to use numbers. It's going to open up a copy of that. Download a copy of that flight I just designed as a spreadsheet style data set. And then I can manipulate that in a spreadsheet program, or I've also written a script that allows you to then correct the flight heights with whatever elevation map you want. So the elevation map that I showed you before, this is now visualized as a hillshade, but this is an elevation map from the Rumble Spatial Data Platform. It's a 1 meter LiDAR derived elevation map. It gives you a fantastic amount of detail, including this little mining test pit there on the hillside. So this is a much better basis for correcting waypoints for terrain following than the built-in one in Lychee, and it's accessible to anybody because it's hosted online. So I can actually use that DEM without downloading it via the cloud-based GeoTIFF functionality that we've built into our platform. Okay, so to use this script, we're going to import a couple of libraries, the reader, raster, and RGDAL packages. And we're going to read in a copy of that demo flight that we just downloaded from Lychee Mission Hub. This is also in the data that I shared on GitHub associated with the webinar. And I'm also going to load the DEM using this raster function. And it's not going to download the whole data set, but it's just going to read the metadata off of the web where it's hosted on Amazon S3. And that usually takes a few seconds to read the elevation data. So I can then type just DEM into the console and get some information. And it tells us, yep, this is a 1 by 1 meter elevation map. It's a pretty big file, 25,000 by 22,000 pixels. And it, importantly, we're going to extract what coordinate system that elevation map is in. It's in a projected coordinate system that's actually different from the flight data that we read in from Lychee. So let's take a look at that flight data in a spreadsheet style format. So this is super simple. It's just like the latitude and longitude of each of these waypoints, the altitude, in this case, that's the altitude above the start, altitude above waypoint 1. heading, and then the curve size. And then these are a few optional parameters that allow you to do things like take a picture at a particular location and things like that. So for the most part, we don't need to worry about any of these columns except for altitude. And what we need to do is correct that altitude field so that it has higher altitudes for higher terrain and lower altitudes for lower terrain. Luckily, that's pretty easy to do with the script that we've got. We want to convert the coordinates that are here in latitude and longitude into corrected coordinates that are compatible with the elevation map. And that's what this little block of code does, using a function called SP_transform. And what we need to do is just make sure that we've got a description of the coordinate reference system for the two different coordinate systems we're working with. We extracted the coordinate reference system information from the DEM here with this proj4 string function. So DEM proj, DEM proj just should be a string. Yep, that's that UTM zone 13 north coordinate system. And so now what we should have is waypoints. Instead of latitude and longitude, they should be in those projected coordinates. We can double check that just by printing the first couple of points. Yep, so those are in those coordinates, and then we're going to use those coordinates to extract values at their locations from the DEM. And that's going to be what waypoint LEV is. And it might take maybe a few seconds. It's got remember, it's sort of reaching out into cyberspace to grab those elevation measures from the cloud. Yeah, and then we can take a look at those. Those look reasonable between about 2,900 and about 29. About 2,850 and about 2,900 meters, which seems reasonable. We want to subtract the first waypoint elevation from this to get the elevation relative to the first waypoint, which is what Lychee requires. And then we want to add that waypoint height back. So we want it to be 110 meters. And then replace the altitude field in the original data with our new heights. And if we go back here, now instead of them all being 110 meters, they're now 110 meters up to about 145 meters, and they come down again to about 110 meters. Because the first waypoint and the last waypoint have identical or about identical, they should have about identical altitudes. So that's great. And then what we can do is, just save this data set to a CSV file that's the same format as the original data. And we can go back to Lychee then and import this file. All right, and we've got a new waypoint mission that's identical to the old one, except now you can see the elevations above each of these waypoints is now updated to follow the terrain, so that we've got, this is going from 110 up to 160 meters, and then coming back down to 110 meters when it's done. So yay, this is great. This means I can save this as Deer Creek Trail demo terrain. And so that's now saved in Lychee Mission Hub. And when I go out to fly in the field, there's an app that I can use to control the drone, also called Lychee, which takes data from that cloud storage location and loads it into the flight control software. So I can go ahead and go out and collect data in the field. So that's the flight planning side of things. I really wish that I could have you guys join me for the practical side of this, where we actually go out to fly in the field. There's unfortunately not good data connectivity to bring a webinar out to that environment, and plus it's about 10 degrees outside, which is not good drone flying weather. But we're about ready to do that as soon as the snow goes away. Okay, so that's about all I've got prepared. But I wanted to answer some questions before we go. Yeah, so Natalia's got 2 good questions. Does Lychee have a good manual or a tutorial? It does, yeah, and I will link to some of those materials in the materials that I share on GitHub. And then Natalia also says, how do you pair your flight path with your drone? That's a great question. I'm going to grab the flight controller so I can show you. The drone that I use for a lot of my work is a DJI Mavic 2, and it's got kind of this is Alice, by the way, and it's got an infrared camera strapped to the front that's made by a company called MapIR. And this is a pretty easy to use system. The controller is kind of a remote controller with joysticks, not too different from a game controller. And in there is also a place to slot in this case, this is an old iPhone that I use for flight control. And if I open up that system, I can actually open up the Lychee app in that's loaded onto the phone, and then I can just load that demo flight, which we just designed. I'll hold that as up the camera. You might be able to see it with a reflection. And so all we need to do is essentially plug in a little lightning cable. Which plugs into the controller and plugs into the drone. Sorry, plugs into the controller, plugs into the phone. And we can turn it on. And we can turn the drone on. And now we're essentially ready to fly. This girl's got lights and camera, and unfortunately I can't fly it indoors. But that's the that's the long and short of it. All right, so we're getting up to the end of our time, and if we've got 1 or 2 more questions, we can address those. Otherwise, I'm going to stop the recording, and feel free to stick around if you've got a specific issue that you want to discuss after the larger group is gone. But thanks so much for coming, guys. This has been fun.